Have you ever stopped to think about how your body makes an army of millions of tiny soldiers every single second just to fight off infections? Well, in this explainer, we're going to dive deep into that fascinating process called granulopoiesis, the making of our white blood cells. We'll follow their journey all the way from a single stem cell to a powerful defense force. This is an absolute must-watch for any medical laboratory scientist or hematology resident out there.
All right, so here's our game plan. We're really building this story from the ground up, so the structure here is super important. We'll kick things off with the basics, why these cells are so critical for our survival. Then we'll take a really close look at the life of a single granulocyte, from its birth to its specialization. After that, we'll get into the incredible logistics behind managing this cellular army. Then we're going to jump into the clinical side of things and see how we actually evaluate this system in the lab. And finally, we'll wrap it all up with some pathology and a few advanced concepts. So, let's get right to it.
Okay, let's kick things off with our first section, Introduction, the Essential Defense. This is where we're going to lay the foundation for understanding just how incredibly vital granulocytes are to our entire immune system. So our topic today is granulopoiesis, from stem cell to defense mechanism. This really stunning image shows a granulocyte squeezing its way through a sea of red blood cells. We're going to follow this cell's journey from its very beginning as a stem cell, all the way to becoming a key player in our immune defense. Now, this explainer is designed specifically for medical laboratory scientists and hematology residents, so you know we're going to be getting into all the important details.
So what exactly is granulopoiesis? Well, as you can see here, it's the whole process of making and releasing granulocytes from our bone marrow. It's actually a key part of a bigger process called myelopoiesis, which is the production of all myeloid cells, including our red cells and platelets. But why is this specific process so important? Honestly, without it, our bodies lose their first line of defense. A tiny infection could spiral into life-threatening sepsis. The diagram on the right shows this in action. You can see a granulocyte literally gobbling up bacteria. And just take a look at that pie chart. Neutrophils, which are a type of granulocyte, make up a whopping 60% of our white blood cells, and their main job? Fighting off bacteria and fungi.
Okay, now that we've got the basics down, let's actually follow the life of a granulocyte, from its very origin right through to its final specialized form.
So, where do these cells even come from? It all begins with a single hematopoietic stem cell, or HSC. As this diagram shows, this one cell has the amazing potential to become many, many different types of blood cells. So what makes it decide to become a granulocyte? Well, it all comes down to genetics. Specific transcription factors like PU1 and CEBPα act like master genetic switches. They essentially flip a switch that tells the cell which path to take. They're saying, hey, you're going to become a granulocyte, not a red blood cell or a lymphocyte. And from that point on, the cell's committed to its journey of becoming a neutrophil, an eosinophil, or basophil. Once that cell has its orders, it enters what we call the proliferative phase. This is where the cell starts dividing and developing its key features. First up, we have the myeloblast, a very young cell with a large nucleus and, importantly, no granules yet. Next up is the promyelocyte, and this is where it starts to develop its first set of weapons. These are the primary or azurophilic granules. Finally, we have the myelocyte. And what's really fascinating here is that this is the stage where the secondary granules appear, and it's the very last stage where the cell can still divide.
After that myelocyte stage, the cell enters the maturation phase. And as the icon here shows, these cells can no longer divide. Their only job from here on out is to get ready for battle. First, we see the metamyelocyte, which has a distinctive kidney bean-shaped nucleus. Then comes the band neutrophil, which has that classic horseshoe-shaped nucleus. You know, you don't typically see many of these in a normal blood sample, but their numbers skyrocket during an infection. And finally, we have the fully mature segmented neutrophil, a powerful warrior with a multi-lobed nucleus, totally ready to fight off invaders.
So, we've just seen how a single granulocyte is made, but now let's zoom out and look at the bigger picture. How our bodies manage this absolutely massive army of cells.
The numbers we're talking about here are just mind-boggling. Our bodies produce about 100 billion neutrophils every single day. That's up to 2 million every second. The slide shows this as an assembly line in the bone marrow, where it takes about 10 to 14 days for a cell to fully mature. Then they hit the highway of our bloodstream. But they're not there for long. Their half-life is only about 6 to 8 hours. Their real work happens in our tissues, where they spend a day or two fighting off infections before they die.
So, how does the body manage this constant production and deployment? It's pretty clever, actually. The bone marrow is divided into different compartments.
You have the proliferative pool, where the new cells are being made. And then there's the storage pool, which is basically a giant warehouse full of ready-to-go soldiers. And here's the really amazing part. This storage pool is 5 to 10 times larger than the number of neutrophils actually circulating in our blood at any given moment. This means we have a massive reserve force that can be deployed instantly to fight off an infection.
Okay, so what actually triggers the release of all these neutrophils from that storage pool? It's all controlled by a really elegant feedback loop involving a molecule called GCSF. When we get an infection, our bodies release signaling molecules that tell the bone marrow to pump out more GCSF. GCSF then acts like a master regulator, telling the bone marrow to ramp up production, speed up maturation, and release those reserves. This can increase the number of neutrophils in our blood by 5 to 10 times, giving us a powerful boost to fight the infection. And once the infection is under control, the signal turns off and everything goes back to normal.
All right, now that we've covered the biology, let's switch gears and move on to the clinical side of things. In this section, we're going to look at how we can actually see and measure the body's response to infection right there in the lab.
This slide shows us exactly what a left shift looks like under the microscope. This is what happens when our body is so desperate to fight a severe infection that it starts releasing immature neutrophils. On the left, you see a normal blood smear with nice, mature segmented neutrophils. But look at the image on the right. You can see the difference immediately. We've got a band neutrophil with its C-shaped nucleus, you can see those darker toxic granules, and there's even a doly body. These are all classic signs that the body is under serious stress and is mobilizing all of its defenses.
Now, when it comes to making clinical decisions, percentages don't tell the whole story. We really need to know the absolute neutrophil count, or ANC. This tells us the actual number of fighting cells that are available. The formula itself is pretty simple. You just take the total white blood cell count and multiply it by the percentage of neutrophils and bands combined. Let's walk through the example here. The patient has a WBC of 12.0 with 70% neutrophils and 5% bands. So we multiply 12.0 by 0.75, which gives us an ANC of 9.0. This is clearly above the normal range, and it tells us the patient's body is actively fighting off an infection.
Okay, in our final section, we're going to explore what happens when things go wrong. We'll look at a range of different pathologies and advanced concepts, from pretty simple disorders all the way to the most serious, malignancy.
First, let's talk about quantitative disorders. This is when the number of neutrophils is either too high or too low. As this thermometer graphic shows, a normal count is somewhere between 1.5 and 7.5. Anything above that, we call neutrophilia, which can be caused by things like an infection or even just stress. Anything below that is neutropenia, which can be caused by chemotherapy or other medical conditions. But the real danger zone is when that count drops below 0.5. At this point, the patient is at an extremely high risk of a serious infection from their own body's bacteria and often needs to be put in protective isolation.
You know, it's not just about the number of neutrophils. We also have to look very closely at what they look like. Their morphology gives us huge clues. On the left, we have hypersegmentation, where the neutrophil has way too many lobes. This is a classic sign of a B12 or folate deficiency. In the middle, we have the Pelger-Hewitt anomaly, where the nucleus only has 2 lobes. This can be a harmless inherited trait, or it can be a sign of a more serious condition like myelodysplasia. And on the right, we have Chidiac-Higashi syndrome. This is a rare genetic disorder that causes these giant granules to form inside the cell, which really impairs its ability to kill bacteria.
Now let's talk about the most serious condition, acute myeloid leukemia, or AML. The telltale sign of AML is having more than 20% blasts. These are very immature cells in the bone marrow or blood. But how do we distinguish AML from just a really severe infection? We look for something called hiatus leukemicus, which really just means the maturation gap. What this means is we see a lot of very young cells, and we see some mature cells, but we see almost none of the intermediate stages. That gap is a clear, ominous sign of leukemia.
Let's touch on 2 more advanced concepts. First, the microenvironment of the bone marrow. The diagram on the left shows how these stromal cells create a niche that keeps our stem cells safe and in a state of readiness. If this niche gets disrupted, it can lead to all kinds of problems. Second, we have the ME ratio, which compares the number of myeloid precursors to erythroid precursors in the bone marrow. As the graph shows, a normal ratio is about 3 to 1. In an infection, it can go up to 6 to 1. But in leukemia, it can shoot up to 20 to 1 or even higher, which is a massive red flag.
So, to wrap everything up, let's just quickly review the 4 pillars of granulopoiesis. First, the origin. It's all about genetics. Second, the process. It's a 14-day journey of maturation. Third, the logistics. They're just incredible, with that massive storage pool ready for action. And fourth, the clinical evaluation, which is absolutely key for diagnosing problems. And let's not forget the most amazing fact of all. Our bodies make 100 billion of these cells every single day. That is a huge investment in our immune defense.